that is thermal energy reservoir. So you can call it as a thermal energy reservoir. So the thermal energy reservoir is nothing but it is a body of infinite heat capacity. Thermal energy reservoir is nothing but it is a body of infinite heat capacity. It is a large body of infinite heat capacity which is capable of absorbing or rejecting an unlimited quantity of heat. Which is capable of absorbing or rejecting unlimited quantity of heat but without suffering appreciable changes in the thermodynamic coordinates. So the boiler, this is a thermal energy reservoir. Condenser, this is also the thermal energy reservoir, right? So here if you add any amount to this thermal energy reservoir, it is a large body of infinite capacity. That means when you add amount of heat, there should not be any appreciable changes occurring in this boiler. Example is you can take it as a furnace, right? Whereas the condenser here, whatever the heat is rejected from this system, that heat rejection, that means here the water is going to be added in the ocean. Say suppose if we add some gallons of a water or liters of a water in the ocean, there will not be any appreciable rise in the level of the ocean. So that is what thermal energy reservoir is nothing but it is a large body of infinite heat capacity. When you add or remove the heat from the system, there will not be any appreciable changes occurring into the energy reservoir. So this changes that do take place in the large body as heat enters or leaves are so very slow and so very minute, and that all the processes within it are quasi-static. Quasi-static means which occurs in a infinitely slowly. So that is nothing but the meaning of a thermal energy reservoir. So the thermal energy reservoir, say suppose from which if you are transferring the heat, so if you are transferring the heat, Q1 is transferred to a system. So Q1 is transferring to the system and operating in a heat engine. So this is the heat engine, right? This is the heat engine is called the source. That means here you are giving the heat and the thermal energy reservoir to which the heat Q2. So this is the Q2 heat. This is the Q2 heat rejected from the system during the cycle is the sink. So a typical source is nothing but here. A typical source is constant temperature furnace. This is the constant temperature furnace where fuel is continuously burned. Whereas in this case, the river or sea or atmosphere itself, right? So that is what the meaning of this thermal energy reservoir. So in connection with with that one, there is one more thing that we have to observe. So there is mechanical energy reservoir is also there. Thermal energy reservoir, thermal energy reservoir, and mechanical energy reservoir. So it is a large body enclosed by a adiabatic impermeable wall capable of storing the work as a potential energy or kinetic energy, such as a flywheel. So all process of interest within mechanical energy reservoir are quasi-static. So a mechanical energy reservoir receives and delivers mechanical energy quasi-statically. Mechanical energy quasi-statically. So that is what a mechanical energy reservoir is nothing but it is also a large body, right? So that large body is going to store the energy in terms of the kinetic energy or in terms of the potential energy. But that particular storage, when we talk about that storage is almost all, it is essentially quasi-static in nature. So a mechanical energy reservoir receives and delivers mechanical energy quasi-statically, right? So that is what a student has to observe the thermal energy reservoir of the hot source, thermal energy reservoirs of the low temperature sink. It is high temperature source. This is low temperature sink, right? High temperature source, low temperature sink. This is the low temperature sink. This is the high temperature source. So that student has to understand this particular side. Next, the cyclic heat engine. So the cyclic heat engine is nothing but a heat engine device. A heat engine device. This is the heat engine device which is fitted in between the source and the sink. Cyclic. So this observe cyclic. It is the heat engine that is fitted in between the source and the sink, right? And this engine, that is, this is the heat engine which is going to convert heat into the work, which is going to convert heat into the work, right? So this particular reservoir is taking the heat Q1 and rejecting some amount of heat by producing the work. So the classic example is the steam engine. So this is nothing but a steam engine, right? So fuel heats the water, the vapor expands and does work. So here the vapor is going to be expanded. Once the vapor gets expanded and this is going to move in this direction, so you will get some work output. The vapor condenses back into the water again and the cycle repeats. And this vapor, once the expansion is over, this vapor will come back into the condenser and it is going to come out as a liquid, and again with the help of a pump, the liquid will be pumped from lower level to the higher level. So this is nothing but a cyclic in engine. So in this particular cycle, where it is converts the heat energy into the work energy, right? So that a student has to understand. Now coming to the heat engine. So this is the engine. This is the engine, and this is going to take the heat. This is going to take the heat, that is Q1, and this is going to reject the heat Q2 to the cold reservoir, and it is going to produce the work output. So this network output is nothing but equal to Q1 minus Q2, right? So in this heat engine, the all the power output devices. So the power output devices, where you will mention it as a thermal efficiency. You will mention it as a, that is, this is nothing but the eta. Eta is nothing but thermal efficiency. So this is eta, and it is going to indicate the efficiency. Now you are going to find out the thermal efficiency. So this thermal efficiency is nothing but the network output divided by the heat supplied. So what is the heat supplied? This portion will be the heat supplied, right? So this W net is nothing but equal to Q1 minus Q2 divided by Q1. In terms of the temperature, say in terms of the temperature, the efficiency is equal to here, that is in terms of temperature, let me to put it as in brackets, efficiency is equal to T1 minus T2 divided by T1. So this is the T1 and this is the T2, right? So this is how you are going to be able to find out the efficiency of a heat engine, right? So there are a few numerical problems are also connected with this particular content. So that you can easily analyze the efficiency from this particular end. So this is the efficiency, right? Hope the because it is the power output, that is by taking some heat energy, producing the network output by exchanging heat with a another reservoir, that is the cold reservoir, right? So this is the heat engine concept. Next one is that there is a the refrigerator heat pump is there. So this is the heat engine. Next one is this is the refrigerator, air conditioner and heat pump. Refrigerator, air conditioner and heat pump. So what this is going to do, that is here observe the heat engine. This heat is taking, that is this is Q1. This heat is rejecting, that is this is the heat Q2, right? You will get the network output. But to transfer the heat from low temperature reservoir, that is inside the refrigerator. So this is the refrigerator. Refrigerator is nothing but it is the space. This is the space. It is the space to be maintained at a temperature lower than the surrounding. It is a space to be maintained lower than the surroundings. Say suppose if you want to maintain this one as a minus 5 degrees centigrade and the outside is 30 degrees centigrade, right? So now here you have to analyze this particular. Now here the duty is that it has to transfer the heat from low temperature reservoir to the high temperature reservoir. So that is, this is in terms of Q1 and this is in terms of Q2. You have to give some, that means you have to spend some work input. So here the work input is required and here this is the work output, right? So this is the work output and this is the work input. So for this cases, that is for refrigerator, air conditioner and heat pumps, we will mention as the in terms of the coefficient of performance. So for a reversed heat engine, this is the heat engine and this is the reversed heat engine. See here, this is the heat engine, this is the reversed heat engine. The reversed heat engines are nothing but the refrigerator, air conditioners and heat pump. So the reverse heat engine acting as the refrigerator when the purpose is to achieve the maximum heat transfer from the cold reservoir. The measure of that particular success is called the coefficient of a performance, right? So when the purpose here, what is here the purpose here? So this is the purpose. So here, what is the purpose here that you have to understand? What is the purpose here? You need to maintain this 5 minus 5 degrees centigrade. But what is happening? Because the outside is 30 degrees centigrade, when you open the refrigerator door, the outside air is trying to enter into this particular space. If continuously this is entering into this one, you cannot achieve the minus 5 degrees centigrade. For that case, what you have to do, whatever the amount of heat is entering into this refrigerator, with the help of a pump or with the help of a pump, that is you need to you need to pump the whatever the heat entered into this portion with the help of a work input, that it has to be thrown out to this one. So the hot reservoir, if you observe the household refrigerator, there at the back side of the refrigerator there is a condenser tubes are there. If you observe that particular condenser tube, the heat is rejecting. So if you touch these condenser tubes, it is of hot in condition. So here the heat is rejecting, right? So here the heat is rejecting and the desired thing is here the coefficient of performance is nothing but it is defined as the ratio of desired work. It is defined as the ratio of desired work divided by work input. What is the desired work here? This is so this is to be, that means whatever the amount of heat is entering into that one, right? So you have to reject that particular that means you have to take out that particular heat. So the desired effect is, that means you need to focus on to this particular side. So that's why the coefficient of performance for a refrigerator, coefficient of performance for a refrigerator is equal to Q2. See this one, this is the Q2. Q2 divided by work input. So Q2 is nothing but heat transfer from the cold reservoir, that is the heat you have to take out. The network transfer to the refrigerator. So this is the network transfer to the refrigerator. So here this Q1 is nothing but equal to W plus Q2. W plus Q2. This Q1 is nothing but equal to work input plus this Q2, right? So all these things to be joined here. So this is what the work, right? So that is all about the air conditioner. So for air conditioner, refrigerator and heat pump, we will mention in terms of the coefficient of performance. So that the coefficient of performance is defined as the ratio of desired work divided, that is desired work to the work input. Here the desired work is nothing but Q2. Q2 is of interest because you need to maintain as low temperature as possible. That is, as low means if it is designed at minus 5 degrees centigrade, that minus 5 degrees centigrade is to be maintained continuously. Otherwise, the refrigeration purpose is not going to be solved. So that you have to observe here. So this is the refrigerator. This is the refrigerator. Now, in the same way, you can also discuss the air conditioner. So the purpose of air conditioner is nothing but in a room, the room has to be maintained at low temperature compared to the outside temperature. So that is for the air conditioner also you are going to mention it as a coefficient of performance. What is the coefficient of performance of a refrigerator, or what is the coefficient of performance of a air conditioner, or what is the coefficient of performance of a heat pump. So this is all about the conditioner. So the air conditioner, the same thing you can work out it. So let me to write something here. So the air conditioner, that is the COP, is equal to the desired effect. So either you can mention in terms of Q2, this as in terms of, always the notations will be in this one. So most of the times I used to follow this Q2 divided by work input. So that Q2 is nothing but equal to Q2 divided by Q1 minus Q2. So this is a work input. This is Q1 minus Q2, right? So Q1 minus Q2. What is this Q1? This Q1 is nothing but equal to Q2 plus W, right? So this is here. This is W. This is Q. This is Q, right? So Q2 divided by, and here this Q1 is nothing but equal to Q2 plus W, right? So this is how, in terms of the temperatures, say sometimes the temperatures are going to be mentioned. So this is T2 divided, this is, in terms of this one, it is the T2 divided by T1 minus T2. So that observe. So sometimes this is a T2, this is a T1, right? Or it is the TH, this is TC, TCR, TL, TCR, TL. The notations will be like this one, right? So either of the notations you can follow. So that is in terms of the temperature, coefficient of performance is nothing but you have to find like this one. That is for a ideal Carnot reverse Carnot engine. Say if it is a reverse Carnot engine, then you have to use this particular formula. For a reversed Carnot heat engine, reversed Carnot heat engine, this is the formula you have to use. So coefficient of a refrigerator or coefficient of air conditioner, that you can observe. So the same thing, right? So that is the air conditioner. Next, we will move on to the heat pump. So the heat pump, the significance of this heat pump is nothing but, especially in winter season, that is in the areas Himachal Pradesh, Jammu Kashmir, that is northeastern states, where the outside temperature is lower, and the body is not going to accept that lower temperature. So in that cases where you need to maintain the room heaters, right? So this is the heat reservoir. So for the heat pump also you need to mention the coefficient of performance of a heat pump. So the coefficient of a performance of a heat pump is equal to, so here also this is the notation Q1, this is the notation Q2. And in terms of the temperatures, so this is the T1, or this is the TH, and this is the TL, right? T2, or write it as a T2, and this is the TL, low temperature reservoir, right? So in that case, the coefficient of a performance is equal to, so in terms of the heat, because here this is the desired effect. This is the desired effect. That means the outside is, say suppose the outside atmosphere is -5 degrees centigrade, and the body is not going to accept this -5 degrees centigrade all the time. So you need to sit in a room, and that room has to be maintained 30 degrees centigrade. So 30 degrees centigrade is the acceptable temperature to the body, right? So, but here what is happening? The heat, if it is a perfectly insulated, no problem. But what is going to happen? If you open the door or if you open the window, so this -5 degrees centigrade heat is entering to this one. If -5 degrees centigrade heat is entered into this room, then you cannot maintain this 30 degrees centigrade inside the room. In that case, then you have to use so to transfer the heat from low temperature reservoir to the high temperature reservoir, you need to give some work input. That means you have to spend some work input to the heat pump, so that this is going to perform the desired effect. So here the room heater, the desired effect is nothing but Q1. So that Q1 is nothing but equal to desired effect divided by work input, divided by work input. So that is nothing but equal to Q1 divided by the Q1 minus Q2. So this is Q1 minus Q2, Q1 minus Q2. Or if it is the coefficient of a performance of a reversed reversed heat engine, right? Reversed heat engine, heat pump or reversed heat engine, or reversed Carnot heat engine, reversed Carnot heat engine. So coefficient of performance of in this. So what that is, you have to use T1 by T1 minus T2. When a word of Carnot is there, when a word of Carnot is there, then most of the times you have to think of this particular T1, T1 by T2, T1 minus T2, right? So here the heat, when you talk about this heat, Q is nothing but equal to, you should have to think of to this Q1 is nothing but MCP, that is MCP delta T. MCP delta T. So try to observe this particular things while solving the problem, right? So Q1 divided by Q1 minus Q2, right? So what is this Q1? This Q1 is nothing but equal to Q2 plus W, right? So Q2 plus W. Now coefficient of performance of a heat pump is equal to, what is this Q1? What is this Q1? Q1 can be written as in terms of Q2 plus W. Q2 plus W divided by Q1 minus Q2. Q1 minus Q2, right? Right? So how you are going to do this particular thing? So that is Q2 divided by Q1 minus Q2 plus W divided by Q1 minus Q2. So this you can write, this is nothing but coefficient of performance of the refrigerator. So coefficient of performance of the refrigerator, and this is nothing but this Q1 minus Q2 is also nothing but equal to W. This W cancel. So coefficient of performance of the heat pump is always greater than 1. So coefficient of performance of a heat pump is equal to coefficient of performance of a refrigerator plus 1, plus 1. So that also a student has to understand this. So sometimes you may get the derivation. Prove that coefficient of performance of a heat pump is equal to coefficient of performance of a refrigerator plus 1. So that means coefficient of performance of heat pump is always greater than 1. Say coefficient of performance of refrigerator is given 3. Then what about the COP of heat pump? That is COP of heat pump is 3 plus 1. So this is nothing but 4. This is nothing but 4. So this is how you have to solve the problem to this side. Okay, hope these particular things are clear. Coefficient of performance of heat pump is this one. Next one is we will study the second law of thermodynamics. In the second law, there are various persons are also connected to that particular second law. So the authors or the scientists connected to the second law. Now we want to prove that whoever may be the author, then their main intention is proving the second law statements are equivalent, right? So the authors or the persons are different, but the law is the same. That is what so the heat pump is over. Now come to the second statement of second law of a thermodynamics. Statement of second law of a thermodynamics. So what this law is going to indicate? So this law is going to state that this second law of thermodynamics has been enunciated meticulously by Clausius, right? Clausius, and another person is Kelvin and Planck. Kelvin and Planck is slightly Kelvin and Planck is slightly, that is Kelvin Planck statement, we can call it as a Kelvin Planck statement and Clausius statement, right? So Clausius statement and another one is Kelvin Planck statement, right? In slightly different words. See, observe this. Words are different here. Although both the statements are basically identical. So each statement is based on irreversible process. So that you should have to understand. Each statement it is based on the irreversible process. So the difference between the reversible process and irreversible process, that basic concepts we have covered in the